Okay, so hi everyone, and welcome back. Today we have the 8th lecture, and we'll talk about something which might seem initially to be the default, which is to have like PCPs with sublinear amplification, but in fact it's not that immediate as you think. So just to kind of like give context. So take, for example, the Hadamard PCP that we discussed. So, we have this like 3-coloring NP proof, and we encode it via the Hadamard PCP. So we get this exponential size encoding, and now we can just probe, 10 locations and then verify it. So when you think about it, you'd say, well, if you only look at the PCP, at the equation at 10 locations, then probably you are running in really, really, really fast time. But this is actually not necessarily the case. And unless we do additional work, having a PCP in which we only query a very tiny amount of locations doesn't save us any time at all. And we'll see together in this lecture why in previous constructions, what we had was, actually ran slower than the PCP, than the NP proof. Like the PCP, even though we only probe the proof at a very small number of locations, we actually do a lot of work, more than what we had to just like verify an NP witness. And after seeing that, we'll see how we can, well, improve on that and do things exponentially faster. So the idea would be how to design a PCP that we can also verify efficiently, exponentially faster than an NP proof, in terms of time complexity. Okay. So, that's a 2-slide recap of what we've done in the beginning of this week. So we had the Hadamard PCP. I won't go into many of the details, but just like the main idea is that we focus on this particular NP-complete problem, that of satisfying a set of quadratic equations. And we had a PCP using, the Hadamard encoding, and we encoded both the assignment and maybe, the tensors product of the assignment, so we can deal with quadratic terms. And the idea was, to first check all of the equations at once by doing this, bundling the equations into one random linear combination. We checked consistency between the various, the two oracles, and then we did this trick of locally testing the Hadamard encoding in order to know that things are encoded like properly, but there is still this case of what happened, like the test ensures that we are, in proximity to a code word, but not a precise code word, and then we use the local correction property of the Hadamard code to deal with it. And the idea is that, we got something with exponential length, which is a lot, but fantastic locality O of 1. And then yesterday, we saw the Reed-Muller, or the low-degree extension PCP, where we managed to fix the length of the PCP, but on the way we, we increased the locality, which is not exactly what we wanted. So, we showed poly length encoding with polylogarithmic many queries for the same problem of solving quadratic equations. And the idea was to use this, the Reed-Muller code, or the low-degree extension code. And in some sense, so we did that, and we also, reduced into an interactive proof system for the sum check, for a sum check claim. So we just like wrote down the entire interaction tree of an IP4 sum check, and we used Reed-Muller. So let's like to say, maybe like to give a bit of a digest of what happened there. So the idea is that we started with the Hadamard code, which is an extremely long code with amazing locality. And we wanted to, get a better length. So we used the Reed-Muller code, which is a code which has much better length, but the locality is not as good. So in Reed-Muller, the locality is roughly that of a line. And we kind of like set things right, the parameters of Reed-Muller, such that, this entire cube is the linear, this is the total amount of information, and each line is of size which is logarithmic. And so we've gotten something like that. And in some sense, it's nice to think about these, local codes as a combinatorial analog of a PCP. Or equivalently, you can think of a PCP as a combinatorial, as a computational analog of a local code. Why? Because whereas a code, the locality only allow us to, be able to test whether the code is valid or maybe local correct it. In PCP, we can check that the proof is correct and maybe, local correct, maybe do some local correction for some local noise. So I like to think about, and this is this inherent connection between codes which are local and PCPs, and typically you see that in every construction that we have of PCPs, there will always be some underlying code from which we derive this structure. Okay, so so we use the Reed-Muller, and just like to say, some small things. We reduced M equations into checking a single equation by looking, at some pseudo-random linear combination. The reason why we did pseudo-random linear combination as opposed to just a fully random linear combination is because randomness complexity corresponds later to the length of the oracle, and we didn't want to have exponential explosion as we did with Hadamard, so we were more careful regarding this linear combination. And then the nice thing about the Reed-Muller code, or anything which has this nice tensor structure of cube, is that we can do sum check on it. And so, we wanted to do the sum check protocol, but this is a PCP. We don't have a prover to interact with. It's something which is pre-written. So we just, wrote down in the PCP anything that the interactive prover of sum check could possibly say. And then we emulated that thing, and we also used local testing for Reed-Muller using the low degree test that we had last week. Okay, so that's what was last time, and I want to tell you about two directions that are extremely interesting to explore. One of them is, this lecture, which how fine? Well, we have great locality. Either logarithmic locality or, O of one locality in the Hadamard. But we don't want things to be just, if you want to use it for, positive application, maybe for delegation of computation, to compile things into ZK snarks and things along these lines, then an important thing is that we also want things to be efficient in terms of runtime, if we ever want to run this thing, because it's not a great use if you only make 3 queries, but you run in exponential time or anything of this sort. So it's by the way, it couldn't be exponential, that the runtime would be polynomial, but still, you don't want to run in huge polynomial time. So I mean, what's the point with respect to an NP witness if the goal is to do quick verification? So this is what we'll do today. But I also want to mention that, we had Hadamard, which has amazing locality and poor length. And we have the Reed-Muller PCP, which has, good length, but not so great locality. So tomorrow we'll see how to combine the Hadamard PCP with the Reed-Muller PCP to obtain a PCP which is both of polynomial length, and so it takes the length, it inherits the length from the Reed-Muller code, and it would inherit the locality from the Hadamard code. So it would be of polynomial length and O of one locality. So we'll see how to get it tomorrow. But today, the main focus of what we're about to do would be to try to get things to work in a fast way. And the way this happens, it happens in 2 stages. And we'll see exactly how everything proceeds. So this is, the comeback of the complexity avocado. We haven't seen it for quite a while now. And the reason why it returns again is because I want to remind you of this class of NX. It is not as popular as P and NP and P space and NX, but for us it would actually be extremely crucial from 2 different reasons. So just like to remind you, NX is exactly like NP, but where you replace everything poly with exponential. So you think about, you're given an exponential size proof, and you have an exponential time verifier which tries to solve this problem. So like NP for things which are which require exponential one. So okay, so as we said before, we constructed these two PCPs. This is the Hadamard one, and that's the Reed-Muller. You have all the rest of the parameters for your convenience. And today we'll construct, but the point is that both of these PCPs were for the NP-complete language of quadratic equations. Whereas today, instead of like looking at a language which is NP-complete, and therefore we can deal with every language in NP, we will construct a PCP for an exp. So for any language which runs in, non-deterministic exponential time, this huge class. And you might ask why, like, why would we want to do this thing? So before I state the precise theorem that we show, I want to tell you just a little bit about the motivation for why would we want to have. So there are two different motivations which I like to think about. One of them is complexity theoretic. So we define this notion of PCP, and we have a, verifier runs in polynomial time. And so if we're only making, logarithmic many queries, for example, in the size of an exponential size proof. So I'm saying that if we look at the PCP and we restrict all of the parameters to be of polynomial time, then we can actually deal with an exponential size proof. And it's natural to ask this class of PCP, where everyone is running in polynomial time, how large it is. So in terms of complexity theory, it's a way of showing that, we know that IP is equal to P space. And this would show us that, PCP is equal to an X. Well, by PCP, I mean, well, the only restriction on the verifier is that it runs in polynomial time. So it's allowed to make polynomial many queries and use polynomial many randomness, which means that it can access an exponentially sized proof. Okay, so this is the first motivation. We want to understand the complexity of the class PCP. The other motivation is exactly what we mentioned, it's sublinear time verification, because this would be an example of how we can solve a problem of exponential size using polynomial time. Now, obviously, the more interesting question would be how to solve a problem of polynomial size in logarithmic time. And the nice thing is that by taking the ideas that we'll see today and adding some new ones, we can take this PCP for an X and show that it's kind of like gracefully scales down. So you can have, instead of like having polynomial time PCP for an X, you can get a polylog time verification for NP. So these are the two main motivations that I wanted to mention. And what we'll actually show is that for any language in NX, there exists some PCP with perfect completeness, soundness, some constant, whatever you'd like, binary alphabet. The length of the proof would be exponential, which is fine for us. The number of queries is polynomial, and the total number of randomness would be polynomial. So all, something that a polytime verifier is capable of doing. Okay, so some remarks are in order. So just to mention, the length of the proof, exponential is in the correct regime, because since we are allowed to throw polynomially many random bits, then we're not there exists some choice of coins that would randomly probe anything of this exponential size proof. So this makes sense. And again, just to mention that when we say polynomially many queries, one needs to remember that this is exponentially less than the size of the proof. So we only, we have a proof size of which is logarithmic, which is exponential, and we're doing something which is polynomial. So we're actually doing an exponential, we're only probing a tiny portion. Okay, so we'll have this PCP, which crucially will run in poly n time, and that's the key point here. And this is the first time that we'll actually see a PCP which runs faster than the computation itself that we're trying to do. Like for example, if what we want to do with the computation is like coloring a graph, then it would run exponentially faster than the time that it would even take to read the vertices of the graph. Right? So think how spectacular that is. It means that, suppose you have a graph on n vertices, then you'll be able to verify the correctness of the proof regarding this graph in time, which is polylog, which is quite nice. Okay, so before I continue, any questions regarding the motivation and the goal of what we're about to do? Okay, so let's just move on, and let's see what we need in order to achieve, this sublinear time verification. So first of all, we have to consider a problem where the size of the description of the object is much smaller than the computation that we want to do regarding this object. And why is that? It means that we need to have some concise representation of the object. Because if, for example, you're giving me a graph in exponentially many vertices, and it is written down in a way that to access the graph, I need to read something of exponential size, then I'm losing before I even started. But if I have a graph that I can kind of represent its adjacency metrics via this, polynomial time algorithm and get an access in without reading, without performing a large computation, then this is something which will be possible. And we'll see that in a lot of detail. And the second point is that we need to design a PCP verifier that only uses this concise description, and as opposed to writing down everything in the computation. And I'll show you exactly, in the next 5 minutes, exactly what was the problem in other things and what do I mean by concise representation. So, when we dealt with interactive proofs in the other course, then we did see interactive proofs for large classes. So what do I mean by large classes? When we looked at, the number of satisfying assignments that a formula might have, then the total number that we're counting will actually the computation, like the straightforward NP computation, you have to kind of enumerate over all possible assignments. So we did something where we talk about computation that in a straightforward way would involve, this brute force of exponential size. And also when we dealt with, with QQBFs, then we had this, a bunch of quantifiers, whether, they exist and for every, and so again, this is something which refers to a large computation. So the description of the problem was succinct in the sense that, it's just a Boolean function. Like, for example, it's a Boolean function in variables, but the actual computation, the computational problem is something which refers to something which is exponential in description. It is, like counting or having this long list of quantifiers. And when we looked at PCPs, I kind of wanted to make the contrast. Then we looked at very different type of problems, right? So we looked at problems where the computation is roughly the size of the description. So what do I mean by that? When we dealt with quadratic equations, so what did we say? Like, we had these m different polynomials that we wanted to check a satisfying assignment. And so what is the computation? It's, taking each one of these polynomials and finding and checking an assignment A. So suppose you get the witness, you get like this assignment A. So you check that it satisfies the first polynomial, the second one, up to the nth one. So the total number, of steps that we need to do is closely related to just like the size of the object that we're testing, right? So that's it's quite a contrast that we have here. And regarding the second thing, like the PCP that we decide, they operated on the computation and not on the description. So what do I mean by that? So let's consider the PCP that we saw yesterday, right? Just like this, we send the low degree extension, and we send the truth table of a sum check, and then we are, sampling this R and checking the polynomial, and we're running the sum check over this thing. So notice that what did the verifier had to do in this case? So I want to highlight these objects. Let's focus, for example, on this thing. So remember that what this CR, these are like the coefficients. This is the low degree extension of the coefficients of the assignment. And this is something which is of huge size. It's roughly of the size of the entire object. So in fact, what we did, it's not faster than the computation itself. I mean, it's faster than finding an assignment and enumerating over all of them, but the process itself of checking an assignment, it's exactly like we're doing in just to compute this these coefficients. It's something which takes roughly the same time as it would take to check an assignment. So just that the verification would take us something which is, at least linear in the description. And in fact, it's like polynomial time. Okay, so what does this mean? It means that we need to find this problem in an X, which is complete for an X. So any problem in an X can be captured by this problem, can be solved if you can solve this problem. But this problem should have some succinct access. So we should have some polynomial time algorithm that can give information regarding an exponential sized object. Now, by the way, this is not as surprising as it might seem, because whenever we have nicely structured objects, then we can have a concise representation for something huge. So for example, I can give you just a constant number of coefficients of a polynomial, and this would describe, and if you evaluate it over like a huge field, then even though I just specify a small number of coefficients, it in fact represents a truth table of a huge function, right? Like, so if you kind of like go back even to the univariate case where I specify, 3 points of some polynomial, then by specifying these 3 points that determine some polynomial, I'm actually giving you all the information to evaluate, some object over, any finite field of your choice. So a concise representation is not surprising, but it's something that will be done carefully. So now this is exactly what I want to show. I want to show you a NX complete problem, a problem that if you can solve this problem, you can solve any problem in an X, but one which admits extremely succinct description. So you can access the problem and talk about it without doing anything in exponential time. So you can run in polynomial time and yet access the exponential size object. Okay, and as always, please feel free to interrupt me if anything is not clear. So this is an overwhelmingly large and cumbersome definition of something which is not that hard at all, but we need to sweat some point, so why not now? So it's called Oracle Sat, which might not be the best name. So I want to tell you, let me parse this thing for you and do it in steps so it wouldn't look so long and tedious. So first of all, we're talking about an input which consists of m, n, and some phi. And I want you to think of this. Oh, what happened? Okay, sorry for that. Okay, and I want you to think about this m as roughly 2 to the m would be clauses, and n would be representing 2 to the n variables, and this would be some formula. It's not exactly what will happen. You'll see in a second that this is just approximately what happens, but let's begin with that. I think it would help the intuition. So we have this like huge exponential size Boolean formula. think about, a 3 sat over, I don't know, like over, sorry, not over exponential size, but like some large formula over m plus 3n plus 3. You'll see exactly what it means. And what we want to check is whether there exists an assignment of exponentially many variables. So think about like this assignment, it's some coloring of the hypercube, right? So you have like 2 to the n points in the hypercube, and we label each one of them by 0, 1, 0, 1, 0, 1. So an exponential size assignment. And what we'll do now is we're going to say that we want the following condition to hold. So for every W in M, so think about it roughly as for every clause, and for every 3 variables out of the 2 to the n possible variables, we want this assignment, which kind of W will indicate what is the active clause, V1 to V3 will dictate what are the active variables, and this would be the assignment to this variable. So in some sense, this is a cumbersome definition for a problem that we'll create. So when we'll do this, analysis of this problem, it would yield this problem. So we see it would make sense. Like we're going to now construct a concise representation of this thing. So this is just like to give you some, some intuition as what is this thing. It's just about a way of representing how to check the validity of a huge exponential sized formula. So now everything will, get clear as I show you why this thing is NX complete. So firstly, okay, so let me just like first address the question. So there's a question regarding Wilfred asks why we want this to be 0. So it could be 1 just as well, but we, out of convenience, like we like to think about satisfying assignments as something which equals 0, just because later if we want to, sum a bunch of these things together and we want them to stay 0 as a whole. But it's out of convenience. One can define the opposite. Okay, so first thing, can anyone tell me why this language is in an exp? Why there exists an algorithm where somebody can provide you an exponential size proof and you can run in exponential time and verify it?
Because your witness is A?
Just give me.
Yes, absolutely. Thank you. So exactly. So, like the question is whether there exists some assignment of exponential size which satisfy this thing. So go over, like somebody, the prover could provide me with this exponential size assignment. And given this assignment that the prover gave me, I will run this, exponential computation of this exponential sized formula and check everything. So this problem is enacted in a rather trivial way. Now, as Ida is asking now whether this is actually useful in practice or of theoretical interest, so I want to say no and yes. No, it is definitely not, like as stated, useful in practice. Like it's very far-fetched to find problems that we care about which are in NX. However, what we can do is that when we scale down this type of ideas and look at something which is of polynomial size and can be checked in logarithmic time, then this would be extremely well motivated in practice. And in fact, such proof systems are being deployed in practice. So yeah, so this is the yes and no. Any special non-technical reasons why 3 variables? So that's a good question from Tamar, which the answer is that this 3 is just because we like the Cook-Levin theorem, which reduces to 3 sat, and it's just out of convenience, but one can play with that. Okay, so we know that OSAT is in NX, and I will show that it's NX complete. So what does it mean that it is NX complete? It means that if we can solve this problem, we can solve any other problem in NX, or in other words, It means that we can take, any language in an X that we like, and if it's an X, then there exists some machine, an X machine M that decides it, and we'll show how to reduce it into OSAT. So what are we going to do? So let X be an input to this machine which solves the problem L. So we want to apply the Cook-Levin theorem, right? The Cook-Levin theorem, is a way for us to take a Turing machine M and represent it by some, 3-stat formula, by a 3CNF formula. So we kind of like saying, these are all of the conditions of the computation, and we can capture them via, just some formula in the form of, 3CNF. And what the Cook-Levin theorem guarantees us is 3 conditions. First, it tells us that the formula that we get is satisfiable if and only if the machine would accept X, right? So it's a 3-stat formula that we're getting, and if the machine accepts, if this is like a yes input, then the formula would be satisfiable, and if it is a no input, then the formula would not be satisfiable. This is just because the Cook-Levin theorem kind of like, it gives this constraint of checking anything that the Turing machine checks. Now, the formula would be in size, which is exponential. Like it would be 2 to the poly of X variables, and it would have 2 to the poly X many clauses, right? So just to not worry so much about this 2 to the power of stuff, let's denote by capital N, we'll choose N to be log of capital N. So we'll have this, this way of dealing without all of these factors, just also convenience. And now the point is, and this is maybe the crucial bit of the Cook-Levin theorem, is that it tells that there exists a polynomial size, let me highlight that, circuit that specify the clauses. So what does it mean, right? Like you have this function which can be computed in polynomial time, and it tells you that this function is equal to 1, with respect to variable v1, v2, v3, and these c1s, if and only if the formula contain this clause. So just to kind of unpack what's happening here, this XOR with CI, this is a way of saying, is that X or not X, right? So if CI is 1, then this would mean not X, and if CI is 0, then the XOR would mean X. And so we're taking 3 variables. So this is, just a formal way of writing something like this, x1, x1, or x2, or not x3, this kind of thing. So it's just specifying an instance of a 3-stat formula. So again, what this thing is telling us is that there exists this concise representation where I feed these variables and I'm saying, do I have x1, x7, and x8 participating in one clause? Do I have x1, not x2, not x3 participating in a clause? And this tells me whether it happens or not. By the way, just to remind you why this happened in the Cook-Levin theorem is because we're looking at a Turing machine, and a Turing machine, you have the head of the Turing machine, and at each point in the computation, it only looks at 3 locations, the cell on the left, the cell above, and the cell on the right. So everything is extremely well structured. And therefore, you get this way of arguing about where you are at any point by just referring to your very local neighbor of the head of the Turing machine. Okay, so let me just quickly scan the chat for the questions. Okay, so there's a question regarding the function phi, and whether it is given as a black box or as or some description. So yeah, okay. So and indeed, as you wrote in the chat, yes, it's exactly given by this description. So that's good. And Alexandros is asking regarding the concise representation. So the concise representation would be exactly this thing. It would mean that we'll be able, so the concise representation, we'll see exactly in a second what's happening in, what do I mean by concise representation. It means that we'll be able to check local conditions just in a similar way as we can do it here. So in some sense, this phi, it is as itself this concise representation of a formula, because it's not just like it's a way of, okay, so it is a formula which represents a larger formula, right? So what is happening here, and you'll see in a second when I'll show you the explicit construction. So it's a way of locally accessing and saying, you know, if I consider this particular clause, does these variables participate in this clause? And if I would assign them with this value, whether this particular clause would be, and so it's not like the actual explicit description of formula, it's an implicit description, just as this dx is an implicit polynomial size description of an exponential size circuit. Okay, so, you know, the main thing that we need to check is the following thing. So, you know, if x is in L, then this would only happen if there exists a satisfying assignment such that for any choice of variables, and you know whether they're negated or not, so this would indicate whether this particular clause exists. So for example, you know, if I would get here, you know, 1, 2, 3, 0, 0, 1, then this would indicate whether the clause x1 or x2 or not x3 participates in this formula. And if this is the case, I need to check this condition, which is, you know, use the CIs to negate and just like check whether all of these three values of the assignment are being satisfied, right? So all of that is just a very, you know, technical way of just like locally checking each one of the clauses. Okay, and please let me know if you have any questions regarding these equations. It's cumbersome, but it's important to understand it. In the meanwhile, Morgan is asking, why is it called OSAT? So it's called OSAT because of, you know, the explicit name is Oracle SAT, and one can maybe think about this as an oracle to the function. But honestly, I'm not that crazy about this name. I think maybe succinct SAT or succinctly represented SAT would have been a better name. Okay, so stop me at any time if you have questions. So we stopped exactly here, you know, like we said that like we know that x is in L if there exists some assignment such that all of these local constraints are being satisfied. And now, how do we get the OSAT language? How did we get it to begin with? So what we're doing is we'll apply the Cook-Levin theorem again to dx. So remember that dx is a polynomial time algorithm which gives us access, you know, which it's a polynomial time algorithm which tells us whether a certain clause exists or not. And if it's a polynomial time algorithm, we want to kind of like, we don't want to have an algorithm in our description, and we just want to have a formula. So we use Cook-Levin to write this thing as a Boolean formula too. So fine, we use Cook-Levin, we get this formula psi of polynomial size in x, and this thing would indicate this would be the new like way of locally accessing. So you know, d of x would be equal to 1 only if we have some, you know, w prime here. Well, the previous so dx is equal to 1 if and only if this assignment, all of the conditions in the newest formula that we get psi are being like, you know, are also 1. Maybe it would have been nicer if I would indicate it with zeros, but never mind. Okay, so now how do we get the whole? Sorry.
Can you please tell again? So regarding this formula, so the formula which this circuit is supposed to represent, all of its clauses are 3 clauses, right?
Yes.
Right. And then if we provide it with a clause W, and then V1, V2, and V3, and if this clause is not consist of those three variables, then we automatically give 0 regardless of evaluation, right? And if this clause has exactly those three values, then we look at the evaluation and then we evaluate. Okay.
Exactly. So, you know, like maybe a nice way to think is like to kind of like forget about the C's because they only talk about negation. So it just like tells you, do you have the variables v1, v2, and v3 in the clause? If yes, you indicate it and you have 1, otherwise you have a 0. And now what we did this step is we said, instead of talking about dx, we can talk about another formula that we got from Cook-Levin, and this formula capital is satisfied if and only if like this has a value 1. So if it has value 1, then there exists some satisfying assignment of this new formula. And now OSAT is what happened when you mingle both of these things together and you kind of like put them together, right? So the idea, so we just like put all of these things together. We define this final formula. This is the OSAT formula. And how it is defined, it's exactly as before. But we're saying, you know, we have this variable W, and this W consists of the W prime that we need for psi, and also of the C1, C2, C3, which is why you have this like annoying +3 over here. And we want to check that everything is being satisfied. Okay, so all that happened here, it might like there's a lot of notation going on, but what actually happened is we said, you know, we started with a next machine. We used Cook-Levin to get a formula, and the formula had a concise representation algorithm. So we took this concise representation algorithm and we applied Cook-Levin on that as well. And then we got like one big formula which captures the problem that we started with. That's the whole thing. Okay, so we have that, and now we want to get a PCP for that would run in polynomial time and solve this, you know, exponential size problem. So what we'll do is to use tricks that we've already used before and do things a bit carefully. So what we want to show is that there exists some polynomial time transformation, T, that would do two things. And this by now should look quite familiar, I guess. So the transformation, you know, given some finite, given like the parameters and the formula, it will output some circuit, and the hat here would indicate that this is going to be a polynomial, but we don't need to worry about it now. Some, you know, polynomial of total degree, which is a side of psi. And what we want it is to satisfy is that if, you know, we have a yes instance of OSAT, then it means that there exists some multilinear extension of an assignment, which is Boolean, and it would satisfy the OSAT equation, right? So, you know, all that means is that we started, you know, with this combinatorial problem of saying whether this kind of exists, whether there exists an assignment that would make this thing always 0. And now we're taking the low degree extension over everything. So we make this an arithmetic problem instead of like a combinatorial problem. Just as, you know, when we did it for quadratic equations, then we took assignments, and then we did it for circuits, and we said, you know, this is an AND gate, so let's write it as a polynomial, and so on and so forth. So this is not really new, but but there is actually a nice thing which is going on here, which is this notion of 0 on subcube testing. So what does that mean? In some sense, notice what we want to do here is we want to check that for every W and for every V1, V2, V3, the value of the function would be 0. So think about these W and VI, V2, V3 determining some subcube, this green subcube. And we essentially want to know whether this is a low degree extension of something which takes 0 over all points in this subcube. Right, so again, this diagram is the evaluation. So just to say it again, we started with some, you know, circuit, which was, you know, defined over 0, 1 assignments. Now we extended this 0, 1 assignment circuit, into something which works over a finite field. So it's far larger. And now I want to say we have this hypercube, 0, 1 hypercube, which, because W is 0, 1, it's like an m plus n dimensional Boolean hypercube. Like the vertices are 0, 1, 0, 1, 0, 1. And we want to check whether all of the vertices in the hypercube, but everything here is 0. So before we had statement of the sort of, we combine equations into one equation and we want to see if it's satisfied. In some check, we had something similar, but we wanted to check the sum over a cube. But here we want to check whether the entire subcube is 0. Okay, so just like it's a nice thing to observe that what is happening. And now I'm going to show you, very easily how we do this arithmetization. And this is nothing new. So what we'll do is, we'll take the same arithmetization that we had before the formula. So what does that mean? If I had an AND gate, I will replace it by, x times y, because this really captures the notion of an AND. And if I had an OR gate, then I write, 1 minus the end of the negation, and x, like a negation, would be transformed into 1 minus x. So this is just a way of capturing these logical operations via polynomials. So, we're writing that, and this ensures that this phi, the phi hat, the low degree extension, which like the polynomial that captures this formula, would be of degree at most the size of phi, because each time we do this operation, we only, add the degrees. And obviously, if we're looking at Boolean inputs, if we look here, then it is an extension because it would take the exact same values, but it also allows us to evaluate it over an entire finite field. Okay, so, nothing interesting really happened here. So let's just see that completeness and soundness hold quite trivially. So if we had some satisfying assignment for the original formula, then what does it mean? It means that if we take the, multilinear extension, the extension of A, it would satisfy the Booleanity condition. I mean, it would take the exact same values on the cube, and these were 0, 1 to begin with. So it would look exactly the same. And also, of course, it would, everything inside would be like 0, like the values that this will take would be 0. And if this wasn't a satisfiable instance, then regardless of which multilinear extension you take, one of two things will happen. Either, we're cheating in the sense that we're not giving a Boolean assignment. Maybe we kind of like, we can satisfy the formula by saying, this variable takes the value 7 instead of 0, 1. This was kind of like be syntactically cheating in a sense. Or it means that there has to be, some point in the hypercube which will not be equal to 0. Okay, so it is simple, but because the notation is confusing, please take a second to think about it and let me know if anything needs to be clarified. I'd be happy to go over it again.
Can A hat be affine rather than multilinear?
Sorry?
If to 0, 0, 0, 0, 0, you assign 1, then is A hat still multilinear?
I mean, you see in the next slide exactly what I mean by multilinear. But by multilinear, I mean that this is going to be a polynomial of individual degree 1. And you're right that like it's like technically you can have a free coefficient of 7, and that would make it an affine transformation. But that's how we typically refer to like the multilinear extension is defined as well. So okay, thank you. So it means that the only thing that we need to do, that is left for us to do, is to solve this problem of 0 on subcube. And then let us abstract it so we won't carry all of this horribleness of the definition of OSAT. So you get some oracle access to some low degree function, f from fn to f. Think about h to the n as like being this green subcube. And our goal in life now is just to say, I want to make sure that the function takes the value 0 everywhere on this subcube, right? Just like an abstraction of the problem that we've seen before. And the idea would be, well, we have one tool that is being used in virtually, 90% of all PCP works, which is subject tool. And we try to see how we can, reduce these problems which look similar but are not similar. How can we, suppose that we want to check that every point is 0, but what we want to know, what we are actually able to do is we can check whether the sum is 0, right? And these are a completely different thing. It's like, obviously, if the subcube is completely 0, if like it's a 0 on subcube instance, then if you sum over it would be 0. But you can also get 0 sum in many other ways, just by cancellations and things along this line. So how do we do this reduction? So this is a nice trick to remember, and one which is being used a lot. In some sense, it's being used so often that like the 0 on subcube problem is almost the same as the sum check problem. Like when I think about it in research, I do not make any distinction. Okay, so what we'll do is the following thing. We'll start by just doing, I'm just going to do it a bit more explicitly than yesterday to avoid confusions. So we take this function int, which would be, standing for integer, which would just be a way of associating integers with the elements of H, right? Because the element of H is an element of like some finite field, and maybe they're, they are some polynomials, and so we don't want to think about it. So we take some arbitrary efficient way of like say lexicographical order, and we give each one of the elements in H, we'll identify it with numbers, between 0 and H minus 1. And now what we want to do is we'll define this polynomial here. So let's see what this polynomial is. So it's a polynomial in n variables. Well, what we're doing is, it already looks like a sum check. We are summing over the hypercube. And at each point, we're saying, let's sum over the value of the function. So if, if I didn't have that, then that's exactly the sum check problem. But now I have this addend here that we're adding. And that would be take each variable and raise it to the power of, the element in H. Right? It seems a bit arbitrary. Why would I want to do that? I mean, I'm just like, going over all of the variables, and and I'm just like giving them these different powers. But you'll see in a second that this makes a lot of sense. And the reason being is, first of all, let's start with the obvious thing. If this is a function that is being restricted to the hypercube, it's 0. If it's like a problem where the green hypercube is 0, then this G would be identically the 0 function. Why? Because, it means that all of these coefficients, like these are all of the values in the hypercube, and so it would be 0 times something, 0 times something. So this is like the this would be the 0 polynomial syntactically. And to answer Bogdan's question, in our case, H would be 0, 1, the Boolean hypercube. But here I'm kind of like trying to think about it abstractly, because we'll also later use it in other settings. And I just want to be able to say, remember that we said that 0 on subcube is exactly the same as subject. Yeah. Okay. So, so we know that if like this is 0, then everything is 0. But the point is that if f restricted to the hypercube is not 0, then I want to argue that the polynomial must be the non-zero polynomial. And why? Because there exists at least one element such that f of a1 to an is non-zero. And then we have a live active polynomial in n variables. And then by the Schwartz-Zippel lemma, we know that the probability that this polynomial will take the value 0, as a function, well, I just take a random value here, is a Schwartz-Zippel kind of thing, which is, like the size of the domain times the number of variables divided by the size of the field. Right? So that's the idea. And maybe before I continue, right, that's to say, like, now I want, so this reduced the problem into checking the sum over G. And, you know, our goal, so if we want to know if, like, so to solve whether the hypercube is entirely zero, it suffices to check this sum. And we know that the sum check protocol is a reduction. Well, if we want to check the sum, then we interact with the prover, and then it suffices to just check the value of this function at a single random point, right? So this is like what sum check is giving us. I want to check that the sum of f, the sum of G is zero. And after I interact with the prover, at the end I just evaluate G at a random point. So now, can anyone spot what is missing? So it is acting regarding G being not a random polynomial, and G is not a random polynomial, but it's fine because like the sum check protocol, it is a confusing point, but like sum check, you can give any polynomial of low degree of your choice, and you ask, is an arbitrary polynomial G, you know, the sum over the hypercube is zero, and you know, you send to the prover at each point a random point, random point, random point, random point, and then you need to evaluate this function only at like this random point that you chosen. I hope that makes sense. So did anyone spot what is missing here for us here? So yeah, okay, exactly. So I think that Wilfred kind of like, so the point is that like we have this thing here, right? And we have the r's, and they're to the power of a, right? So what we have here is a function which is being determined. You know, we raise this the variable r to the power of int of a, but we don't have here a low degree polynomial. This is not something that I can evaluate at the point f in the field f. I can only evaluate it in h. So I need to take the low degree extension of that, right? So similarly, as you know, I started with the hypercube, like with 0, 1, I want to be able to evaluate it everywhere on the big cube. Also with respect to this function of like raising to the power of int, I want to be able to evaluate this function for values which are not integers. So what do? I take the low degree extension of R. So just to remind you, what is the low degree extension of R? So you have, this is just Lagrange interpolation. So the Lagrange polynomial, you know, it's the polynomial which indicates whether a certain element takes a certain value. So this is just like a fancy way of saying this is the polynomial that where you have an element a in H, it would give this thing. It's exactly a way of like saying this is a way of extending a cube in the way that would identify on this point. Okay, so we do this thing, and then to kind of like summarize this, all we want to do is to run the sum check protocol on this low degree polynomial. We run it on this low degree polynomial, which is exactly like the G polynomial, but these things are also polynomial, and we evaluate this, we want to run sum check, and for that we need to query it at like one random point, which would be the R values. So that's the whole strategy. So maybe to kind of like say just like one more time that the idea here is we're saying, well, we have this nice way of checking that an entire cube is zero, and the way is by, you know, getting this addend here. So we stick this thing, and it has this like nice property that, you know, if we had zeros in the beginning, then this would be a degenerate polynomial with 0, and otherwise it would be a live polynomial, and everything will work as you expect. And just to see why this works, then how would the actual test look like? So what would happen? We'll have the prover, and the prover would say, you know, for every possible R, just output the like, you know, the entire evaluation table of a sum check protocol for this claim, which is exactly what we want to check. So remember, just to kind of like highlight it, this is a sum check this checks the sum, but the moment that we added this addend here, then this check whether everything is 0. And we want to run sum check on this entire claim. And we'll have the prover specify the entire like prover strategy, and then the verifier in turn samples some randomness, runs sum check and emulates the run of the sum check using by querying the right place of the PCP. So we've seen this trick a lot of times, and then we'll actually make this query to the function to f, which will check it at one place, and we'll also need to evaluate this addend as well, so we can actually evaluate this thing, and we're done. So the completeness and soundness, they would be quite immediate. So let me just say that, and then I'll take some questions. So suppose we started with some function which is all 0 on h to the n, then by our choice of this arithmetization, then we know that this sum is equal to 0. So if we run sum check, then we'll accept. And soundness would tell us that if it isn't 0 or everywhere on h, then except of this small error probability that would come from the Schwartz-Zippel lemma over the choice of the R that we have, we'll have that the sum is not equal to 0, and so the sum check protocol will reject. So that's essentially everything. And the last thing that we need to do is to kind of put these two parts together in a somewhat straightforward way, but it would be maybe a good exercise for us just to see that all of the ideas kind of fit. Any questions regarding this test?
So this proof have sum check table have exponential length.
The proof of the sum check, it would have an exponential length, yeah. And then we'll, I guess maybe we even do it now, yeah. So let's do the proof length just to be sure. So what we'll have is this size of f, which in our case would be polynomial, and then we raise it to the power. So okay, so what is exactly the size of this description? So remember that there are f to the n different choices for the randomness. Like each r is a value from f, so we need to write down answers for all of these possible verifier queries. And each one of them, the size of the polynomial that we're sending, it's f to the n and times h plus d, which are not important terms here. So we get this thing, size of f to the power of n in terms of proof length. And in terms of query complexity, then essentially what is happening, then we have this sum check protocol. It proceeds in n rounds, and in each time of this n rounds, we need to read this many elements, which is what sum check requires, and we'll need one query that we make to f, right? So, and in terms of this running time, because everything we're doing here, it's polynomial from this verifier here, and polynomial by the evaluation of the R1, which is just the multilinear extension. So that's everything that we wanted. And now I just want to tell you sorry?
Back. So in the sum check, we send these polynomials as coefficients, right? The polynomials that prover sends to verifier are sent by coefficients. This univariate polynomial. So inside this proof length, I think we have this f to the n too much. It doesn't matter in this case, but.
So in the proof length, oh, you're saying that we maybe don't need to specify it everywhere, but rather
not by evaluation table, right?
I think that makes sense. Let me double check that offline and just to be sure. It does make sense. Perhaps it's a bit, we're not careful here because we take anyway, this factor, but it might be a bit more efficient. I'll give it a thought and just to double check and not mislead. Thank you. Okay, so last thing that we'll do about 5 minutes of putting everything together, and I think there is even though it's a long protocol, there is an advantage of doing it just because you'll see the zero-sum check happening twice. So by the way, there is one thing which I kind of, hid under the carpet so far and we didn't deal with. Can anyone tell me what is missing? I mean, why can't I just start by saying, let's take this arithmetization to OSAT and then just run the 0 on subcube test with respect to the condition? Where did I lie? What did I didn't tell you yet? So just to maybe to give a small hint, you remember that we said that there are two ways in which the prover can cheat. One, we started with a Boolean function, and we then evaluated over a finite field. So the prover can cheat by giving us something which is not satisfiable, but it can also give us an assignment which is not Boolean. And just because we're considering, this like low degree polynomials and stuff, then you can technically evaluate it. Maybe, if you take an unsatisfiable Boolean equation and you feed 7 in the low degree extension, then things, maybe can go wrong. So we'll also need to add this check. That's the only missing component. So let's see what the protocol is doing. We start by computing the arithmetization of the formula. We still have a formula. We complete compute the arithmetization of it, and then we are outputting this, pi of a, which would be the multilinear extension of the assignment a. By the way, just I feel that I should have mentioned that before. So let me just quickly go back to the slide. When you look at this polynomial, no, this is not what I want to show you. But, okay, I don't see where it is, and we'll shorten time, so I'll do this later. I just wanted to show you that this is a multilinear polynomial, but never mind. I'll show it to you later. So, okay, so and good. Now we have it. So we start again, just to say we arithmetized the formula. We took some satisfying assignment, which is a multilinear extension of 0, 1 to the end. So just like to say, maybe I can't do this, so I have to say it anyway. Why this is a multilinear extension is because if you have a Boolean function and then having quadratic terms, if you have 0 to the power of 2 and have 1 to the power of 2, then it doesn't change. So if you take any polynomial which extends a Boolean values, then all of the terms must be of degree, like each variable must be of degree at most 1, or I mean, it wouldn't change. Regardless of generality, it would be the same, it would evaluate to the same function. Just because, x squared is indifferent between, like, it's the same for 0 and 1. But never mind, this is just an aside. So we send this low degree extension, multilinear extension of the assignment. And then we do the following thing. For every choice of randomness, we'll do the following test. So can anyone parse this for me or have a guess of what this is doing and why did I color, like why is this colored with 2 colors? So what are we trying to test in this condition? Like, does this x times 1 minus x look familiar from something that we've done? Yes, exactly. So as thank you. So as Valerio is saying, this is like, the condition of x 1 minus x equals 0. This is a way for us over the finite field to check whether something is Boolean valued, right? Because if it's 0, then this would evaluate to 0. If it's 1, it could evaluate to 0, and otherwise it wouldn't. So this is like a Booleanity checking. So that's good. And now the second question: why do I have this like purple color here with this R's? Why is it not just like checking the assignment that this sum is equal to 0? And the hint would be that this is a trick that will do a lot of time, that a new trick that we learned that will do a lot of time. So just to say, okay, so this would be what we want to check. We want to check that, yeah, so kind of like what Wilfred is saying, we want to check that the assignment is Boolean for all variables. So we want to check this sum. So this would give us, if I look at it as a sum, it would give us the number of locations. Like it would take 0 wherever an assignment is equal to is Boolean. But whenever the assignment is not Boolean, and I write x times 1 minus x, it could be a large number. It could be any element of the field. Maybe it could be, you know, f minus 7. And then it can have another element, and the sum will cancel. So that by summing over this condition, I'm not guaranteed at all that everything is Boolean. So I don't want to check that the sum over the hypercube is 0. I want to check that every element in this cube is 0. So in fact, what I want to do is I want to run again the 0 on subcube test that we had before, and we do this by adding this addend here, as we saw in the last few slides. So we write down a sum check protocol for that, and then again for the choice for additional randomness, we'll have the sum check protocol, and again look that this is divided into 2 different parts. So we want to check, and the reason being is that we want to check not that the sum of this thing is 0, but we want to check that for every one of these terms, like the entire subcube is equal to 0, because that's the definition of the OSAT problem. And we do this by considering this addend. And we write down this sum check oracle. So now at this point, what are we doing? Like the verifier will go, it would also compute the arithmetization of the problem. And then, it would just sample one like random string. And using this random string, we'll emulate an interaction with the sum check oracle as if this was a prover. And after that point, we'll know that we are Boolean. And then we'll continue and we'll sample some more randomness for the sum check, and we'll use that randomness in order to look at the right locations in the PCP that capture the sum check and emulate the combination and just check that everything works as we had. Okay, so that's the entire protocol, and I'm going to leave you here in the slides just to see, what the soundness error and the proof line, the query complexity, and do all this calculation. Also, if anything is unclear, ask me. But I think that by this point, like the main idea is clear. We saw all of the subcomponents, and it's just about like doing this accounting and checking that everything works. So I will stop the recording now.